Let's just jump right into this explainer. Today, we're investigating the hidden, machine-level reality of C++. You know, as developers, we spend hours agonizing over syntax and logic, right? We write high-level instructions because they're way closer to human language and a lot further from the raw machine code the CPU actually runs. But have you ever stopped to think about the physical, spatial reality of your code? Like, where do these objects actually live? Well, today, we're not just treating C++ as a language, we're looking at it as a living, breathing mechanism.
Instead of just assuming the machine magically works, we're going to pry open the black box. Look, it's easy enough to write a program that compiles and runs without throwing errors, but if you don't understand the physical journey of your data, how memory is allocated, and what happens the exact millisecond you hit run, you're kind of flying blind. So we're going to track those exact milliseconds. We're bridging the gap between that abstract logic you type on your screen and the literal, physical memory addresses inside your hardware. And this brings us to our starting point. Just 2 words and a semicolon. Student S. This right here is our protagonist for today. But seriously, don't let the simplicity fool you. The absolute instant the compiler reads this line, a massively complex sequence of physical memory allocation and initialization kicks off. This single line is basically our forensic evidence. It's the thread we're going to pull on to completely unravel how C++ operates under the hood.
So the crucial thing to grasp is that before this object S even exists in memory, C++ relies on a class to define its exact shape. Think of a class not as the data itself, but as a rigid blueprint. I mean, C++ was originally called C with classes for a very good reason. A class is an abstract data type. This is literally the pillar of abstraction in action. It's telling the compiler, hey, whenever I ask you to create a student, this is exactly how much space you need to carve out, and here is how that space should be partitioned. Without that class blueprint, our object S has absolutely no definition and no existence.
Now, take a look at how this blueprint actually ties attributes and actions together into one distinct measurable block. In older, procedure-oriented programming, data and functions were completely separate, just floating around. But here, our student blueprint bundles the data, things like name, date of birth, and marks, right alongside the functions that actually manipulate them, like total, average, and display. This fundamentally changes how memory is organized. Instead of scattered variables and isolated functions, we get this cohesive, unified data structure that perfectly represents a real-world entity inside the machine.
And by bundling all that together, we're essentially building a fortress around our object. This is encapsulation, one of the absolutely core pillars of object-oriented programming. By default, the data members inside our C++ class are private. They are locked away, totally hidden from the outside world. Why does that matter? Well, it means chaotic global functions can't just swoop in and corrupt your student's marks or name. The only way to interact with that locked-away data is through the public functions, the authorized gateways we defined in our blueprint. It creates incredibly secure code.
Okay, so the exact millisecond the code runs, a special function called a constructor fires automatically to initialize those data members. This is the literal moment of birth for our object S. It gets allocated on the stack, which is this highly organized, automatic memory neighborhood. And because a constructor shares the exact same name as the class, the compiler knows to trigger it the very moment the object is declared. This guarantees our object isn't just taking up space with random, leftover garbage data from whatever app you were running 5 minutes ago. It's initialized and ready from second 0. But wait, what if we don't know how much memory we need in advance? That's where we use the new keyword to dynamically carve out space at runtime. See, the stack neighborhood is incredibly safe and super fast, but it's rigid. Its size has to be known at compile time. So when we need flexible, on-the-fly memory allocation, we step out of that safety and enter a vastly different, totally unstructured neighborhood, the heap. The new operator creates objects dynamically while the program is actively running. But since this memory is out in that vast, chaotic heap, we need a way to keep track of it, or else it's lost forever.
Which brings us to the big question, why do pointers even exist? Well, because in the heap, things get lost. The pointer acts like a glowing wire. It grabs the exact physical memory address of our newly created space and tethers it back to the rest of the program. A pointer isn't just some abstract concept. It's literally a variable holding a physical address. When new creates an object on the heap, it returns that exact location, and our pointer grabs it. If you want to talk to that dynamic object, you have to send a message down that wire. This right here is what gives C++ developers such incredible, low-level power over the hardware.
C++ even lets us throw a tether directly to a specific variable deep inside our object using pointer-to-member syntax. It's wild. This really shows just how surgical and granular C++ memory management gets. That scope resolution operator, those two colons, that allows us to point not just to an entire object, but to a specific, fully qualified data number within a blueprint. It means functions can efficiently access and update specific attributes directly in memory without needing to copy or move massive amounts of data around the system.
Now, to avoid the heavy lifting of copying an entire object, we use reference variables. These create direct aliases to the exact same data object in memory. Think about it. If our student object is absolutely massive, full of grade arrays and large text strings, copying that entire object every single time we pass it to a function would completely bottleneck the CPU. It's a huge waste. A reference variable, which uses that ampersand, creates an alternate name for the exact same physical space. Any change made to the alias instantly happens to the original object because they are literally the exact same bytes in memory. It makes your programs lightning fast.
Let's zoom out for a second. This timeline tracks the complete physical journey of our object, from birth through active communication to its eventual death. We've seen time 1 where the constructor fires and builds the thing. Time 2 is the active life of the object. It's communicating with other objects through message passing, requesting procedures, sharing information. But what happens when the program is done with it? C++ requires strict memory management. The object has to be destroyed to release the memory space. And if that isn't handled correctly, things go horribly, horribly wrong.
Which leads us to what actually causes a memory leak. Well, when we manually allocate memory with that new keyword, we must be the ones to manually sever the tether and free the space using delete. This is crucial. Out in the heap neighborhood, there's no automatic cleanup. If you use new, the machine assumes you need that space forever. If your program loses the pointer to that memory without calling delete, that memory is trapped. It becomes a ghost. That is exactly what a memory leak is, and it's the silent killer of C++ programs. Over time, those leaks build up, eat all your memory, and absolutely crash your system.
Thankfully, for objects created on the stack, like our original student S, we have a built-in safeguard. The moment that object goes out of scope, which just means the function it was living inside finishes running, the compiler implicitly calls the destructor. Think of it as the Grim Reaper of memory. It shares the class name, just like the constructor, but it's marked with a little tilde. It takes no arguments, returns no values. Its entire purpose in life is to sweep the memory clean, ensuring that space is released for future use and preventing those disastrous memory leaks automatically.
Now look at the very real consequence of bad versus good code organization. With procedure-oriented code, we have chaotic global data moving openly, easily corrupted by literally any function. It makes large systems a nightmare to debug. But with structured, object-oriented code, memory is strictly partitioned, data is hidden, access is perfectly controlled, and objects actually handle their own lifecycle. Plus, as your programs grow, OOP allows for inheritance, letting you reuse these secure blueprints and polymorphism so different objects can interact seamlessly without rewriting code. It just models real-world problems so much more effectively.
Ultimately, C++ isn't just about getting some text to print on a screen. It is about having absolute granular control over the hardware. It's about really understanding the profound difference between the stack and the heap, knowing exactly when memory is claimed, and ensuring it is responsibly released. So I'll leave you with this. The next time you type a single simple line of code, ask yourself, do you truly know where it lives and where it dies?